Hey guys, let's talk IMFs. So, intermolecular forces, even before we started cutting content and changing the exam format and doing all of those things, was listed by the College Board as the most important unit in the AP chemistry curriculum. You were supposed to spend the most days on it. You were supposed to spend the most time on it. It was the most tested thing. We did spend a lot of time and days on it. We did practice it a lot. It's something that we cover to a pretty good degree, like intro in lots of different ways in the bonding unit, but I was also thinking of during first year chemistry. So the most important thing here is when you are talking about this or writing about this, because we are going to have to write about this. There used to be a known quantity on the AP exam that question one was always about equilibrium. Well, no matter what happens on this test, you are going to have something related to IMFs. So IMFs, it's important to remember that they're relatively weak attractions and they're related to physical properties. So that means things like melting point, boiling point, state of matter, um, the ability to dissolve, so solubility, vapor pressure, things of that nature. So it's not whether it reacts or not. So the most important thing from this first slide is when we're talking about those things, we are using either the phrase IMF or intermolecular force. Do not use the word bond. And do not think about this when you're talking about the chemical change or a chemical reaction. So if we're talking about water turning into hydrogen and oxygen, that's chemical bonds. That is changing from one substance to another substance. But when we're talking about water turning into ice or steam, that's all still the same substance. And those are IMFs. So it's within the molecule as a bond, between them as IMFs. They used to have you draw those a lot. I don't think we're going to have to draw them, but it's very likely you could be doing some labeling. So back through bonds, we already did a bonding day. Ionic bonds are positive and negatively charged ions. Covalent bonds are two nonmetals sharing electrons. The attractions, once again, the opposite charge. Metallic bonds is a metal with another metal. That's what gives them all their unique properties. The electrons are freely moving. That allows electricity to be conducted. It makes them malleable. It makes them ductile. If we're talking about bonds, once again, we are using, so you should have this on your bonding one, but it also could be on your IMS here, Coulomb's law. You won't have to do a calculation. How strong that attraction is related to how big the charges are. This also relates to IMFs and how big the distance is between them. So Coulomb's law, Coulombic attractions works for IMFs and works for bonds. So you won't necessarily have to say Coulomb's law. You won't have to use the equation. I'd be surprised if Coulombic does not show up in some way or another, but definitely talking about attractions. And with attractions, it's charge and distance. So we've already done all of this. With covalent, you could be drawing Lewis structures. Probably something was shaped. And then you can learn how the bond leads to the IMFs. For ionic, we talk about the size of the charge, plus 1, 2, or 3, the size of the ion, whether it's small like lithium or bigger like rubidium. With ionic, and the reason that we're putting this here is all of the particles within an ionic compound are held together by an ionic bond. So ionic bonds don't really get into IMFs until we start talking about mixtures, which are right here. So IMFs are more or less reserved for covalent compounds. So just wanted to kind of bring bonding back in so that we could see and think about that. The only time that this really relates to ionic bonds is when ionic compounds dissolve in a liquid. We'll talk about those attractions, but that's ionic bonding is different. Metallic bonding, we are talking about pure metals, we were talking about alloys, we were talking about those properties that I listed there. So an important thing, if you're asked to compare something like sodium chloride to H2O, when you're comparing the properties of sodium chloride, we're talking about ionic bonds, super strong. H2O is a covalent compound held together by strong covalent bonds, but its properties are determined by IMFs. So that's an important contrast there. So to get more specifically into IMFs, we know that they're between covalent bonds molecules. Sorry, it is different. And these are some of the properties. State of matter, like I said, is also another big one. So you want to have all 6 of these written on your cheat sheet. You want to maybe have this slide or parts of this. You don't want to print out the whole document because we don't want to have so much stuff that we can't find it. But know so that you could list what the IMFs are. Is it between polar things, non-polar things? Right there is where I said ions become involved. So we're going to be going through these in more detail, but right there is our summary. We're looking at what is the compound. So polarity is huge in terms of explanation. That would be the other thing. If I had to bet on explanation today too, I will start to make some bets on this. But things are polar when they are asymmetrical. And a phrase you want to use with that, and I've tried to say it on the videos for you and the feedback from mock exam, is that the dipoles do not cancel. The reason that it is asymmetrical is because of lone pairs or different elements, but that's not the full explanation. It's asymmetrical, so the dipoles don't cancel and the electrons are distributed unequally. Nonpolar are symmetrical. The dipoles do cancel. The electrons are distributed equally. And in general, even if it doesn't look totally symmetrical, things that are hydrocarbons are nonpolar. That bond is right at the edge of polarity, but the way that they spread out usually makes it nonpolar. And then we know an ion would be from an ionic compound, but anytime we have a charged atom, a metal that's with a positive charge or a nonmetal that has a negative charge. So to go through the details of each type, once again, I don't have to read each detail on here. I know you can do that, and I know you probably can zoom through these things a little bit faster, but the only time you should be using the word bond if we are talking about physical properties and IMFs is for hydrogen bonds. For dipole, and all of the others, they have bonds. This is not a bond, but somebody, I always blame biologists, named it hydrogen bonding. It is just an extra strong dipole. It happens when the H is directly connected to an N or F. So it's the H on one thing, and that H has to be on an N or F as it attracts to an N or F on another molecule that has some bare electrons on it. It is in general the strongest of the IMFs because it has the biggest partial charge. So if we go back to Coulomb's law, it's about how big your charges are. Well, this is the most polar that a polar thing can be because we have our highest electronegativity elements. We have hydrogen on the other side with just that one electron being stolen away from it. Dipole attractions happen whenever we have that asymmetry or lack of canceling of dipoles, which leads our molecule to be polar. It has a permanent dipole. So these are good phrases to hear a lot more. So the opposites attract. It is a permanent positive and negative charge, and they attract each other. So polar molecules stick together like that. I said ionic compounds don't have IMFs, and they don't by themselves. But when an ionic compound is mixed with a covalent compound, that's when we start to use the IMF phrase. So the attraction between something like water, a polar thing, and a sodium ion or sodium chloride is called an ion to dipole attraction. That's what allows it to dissolve because there's an attraction between the partial charge on the polar molecule and the charge on the ion. They attract one another. And a specific part about this is that attraction is not stronger than the ionic bond holding the sodium chloride together. It's only when it's totally surrounded and there's a whole bunch of these ion dipole attractions is it strong enough to overcome them. So when we talk about solubility later on, it's all about the IMFs or bonds that we're breaking, the IMFs that we're making. So that's what it is that in total, these IMFs are strong enough to overcome the separation. An ion to induced dipole is when we have a charged thing, and then it comes next to something that is not charged, so a nonpolar molecule, and in this case it's positive, that would pull electrons towards it to make that nonpolar thing temporarily polar. That's what induced means. We have forced something to temporarily happen that wouldn't have happened on its own or wasn't happening on its own. can induce vomiting or labors when you're starting something. This is like if we take a balloon, rub it on our hair, well, your hair, and stick it to a wall. The balloon had a charge and then it stuck to the wall, not because all of a sudden the wall is full of electricity, but because the electrons line up differently, temporarily making a dipole, allowing those things to attract one another. We often say that polar and nonpolar don't mix. We say phrases like dissolves like. Those are not, I'll say this later, not explanations. Those are statements. Those can help us remember things, but that should not be your explanation for anything. Especially because there is an attraction between polar and nonpolar things. When I've got an O2 all by itself, the oxygen on the right and the left are attracting each other and attracting the electrons equally, so it's totally nonpolar. Well, water is very polar with negative end over here, positive end over here, and what happens is those the negative part of polarity pushes the electrons away, and it temporarily induces a dipole. So it's very much like when we put that ion next to a nonpolar thing, it pushes and pulls the electrons to temporarily make it polar. Well, a polar thing can do that as well, temporarily making some nonpolar thing have partial charges. There is an attraction between oil and water. It's just kind of temporary and weak. Probably the king or most important of these, we always say, well, hydrogen bonds are the strongest, so maybe they're the best, but no, LDFs are the most important. We could write in a lot more details induced dipole to induced dipole, but that's way more than you need to write. Right, but it's the attraction between our nonpolar molecules. It's because it starts by electrons just randomly moving around. So we say in a nonpolar molecule, the electrons are being shared equally, but really they are on average being shared equally, and they're just moving randomly. And that random motion isn't pulled more one way than the other, so it ends up being equal. Well, at any moment right here, for example, those two electrons show up on the same side. That side ends up being temporarily negative. Well, those electrons, once they show up here, they start pushing on the electrons that are here and attracting to the nucleus that is over here. So this temporary random dipole forces this other one to also temporarily be a dipole. And then those two attract one another. We've said this before, I'll say it again later. But when you're listing IMFs, all covalent molecules have IMFs. So every single thing, LDFs, all of them have IMFs, not LDFs. So you would list this along with dipoles and everything else. So once again, we can have an ion either attract to something polar or nonpolar. We can have a O or an H that's on an N, O, or F attract to another H that's on an N, O, or F. We can have a polar thing attract to a polar thing, a nonpolar thing attract to a nonpolar thing, or even a polar thing attract to a nonpolar thing. And it is all about opposite charges attracting, just what's causing and how permanent is the opposite charges. So once again, I said I'd say this a lot because you don't want to miss this easy point. Everything has LDFs. Polar molecules have dipole. If it has an H that's on an N or F, it has hydrogen bonding. And we only talk about IMFs for ionic compounds when they're mixed with something polar or nonpolar, but they can attract to both of those. So we've got some quick pictures here. You can pause and answer it. Obviously, that's what happens a lot in like the videos we're watching for kindergarten. But I know you guys are just kind of skipping through this, getting a quick refresher. So here, that's an H and an F, an H and an F. That's a dipole. Here, when I have an atom bonded to itself, it's nonpolar. So that's nonpolar and nonpolar. That is a LDF only. So here, this would have hydrogen bonds, dipole, and LDFs. This would only have LDFs. Right there, that is an ion to water. So that would be ion dipole. Here, sulfur with oxygens. So that is polar because the molecule is asymmetrical. It looks like water, but we've got to look at our answer key here. So it's dipole, the dipole with also LDFs. We don't list LDFs up here. You can argue whether they're there or not, but they don't expect that in the answer. So the reasons we do this with IMFs, usually the first point is just say what types of IMFs are there, and then we use those IMFs to explain physical properties, compare physical properties, and predict physical properties. Sometimes we are looking at data, sometimes we are taking information to predict what the data will be. So the type of IMF is just based upon what thing is there. Is it polar or not? Is there an H or not? But the strength has to do with multiple things. It comes from the Q part of Coulomb's law, Q1, Q2. So how big are my positives and negatives? For a polar molecule, it's how big is the electronegativity difference. You could print out a periodic table with electronegativity values, but you're not going to need to know specific values. It's just the farther apart the elements are on the periodic table, the more polar it is. So H and F's about the most polar of a covalent bond that we can have, which is why that hydrogen bond ends up being crazy strong or a very, very strong IMF. But this was the other word, and this is a key word. Use this word. Just like symmetry and dipoles for polarity, we're going to use polarizability because that's what describes the strengths of LDFs. So the word of the day, this was the word of the day when we were together. It's the word of the day again. It is the amount of distortion of your electron cloud. You don't need to define it. You just need to know that it's how polar can your nonpolar thing be? And it's based on having more electrons. So when you look at a compound that's got a whole bunch of atoms and a whole bunch of bonds, it's very polarizable. Molar mass is our shortcut for this. It's not because the mass makes it more polarizable. It's because things with lots of mass have lots of electrons. So when you're looking at molar mass, you're just saying to yourself, oh, there's lots of electrons, so it's very polarizable. So that could make your LDFs very, very, very strong, which is what I was going to get here. If we were on a level playing field, the same molecule across the board, the same size, so same distance, because of bigger Qs, a hydrogen bond would be stronger than the dipole attraction or an LDF. But those large molecules can get really, really polarized or polarizable and have really strong LDFs. Water has hydrogen bonds. It's one of the strongest things in terms of hydrogen bonds because of its size and because of how polar that can be. But it's a liquid. This is where we're going to say data. Solids have stronger IMFs, and there are non-polar things that are solids. Wax is an example. So if something is a solid, that proves that it's sticking together better and proves that its IMFs are stronger than a liquid or a gas. So that tells us, okay, those LDFs must be stronger. So we look beyond the IMF type. Right here, this statement is fair if the electrons are about the same number. So when I compare H2O, which has two H's, 2 electrons, O has 8 electrons, 10 electrons right there. When I compare it to CH4, so 4 plus 6, 10 electrons, those have the exact same number of electrons, so their LDFs are very, very close to one another. They're about the same polarizability. CH4 is non-polar, so it only has LDFs. H2O is polar. H2O has H's bonded to O's, so it gets even stronger. So this is a true statement with the same number of electrons. But once you start to compare or have different number of electrons, it becomes trickier or less true. And that's where we use data. Strong IMFs, and those could be from hydrogen bonds or it could be from really strong LDFs, would be a high melting point or a high boiling point. So sometimes you just give melting and boiling points. A more condensed state means the more solid it is, the stronger its IMFs. Liquids are kind of in between. They're close together, but still freely moving, whereas solids are stuck in place. Gases are far apart. They're experiencing little to no IMFs. A low vapor pressure means that vapor pressure comes from when a liquid that's evaporating. Low vapor pressure means very few particles up here because they're all still stuck down here. Hot, so that is actually, that's a strong IMF here, and I forgot to correct it, but it's not going to get corrected during this video. High volatility. Volatility is like how smelly it is or how easily it becomes Vaporized, sorry. So it's really a low volatilities when it sticks together. High surface tension, we know water has a high surface tension. It's just in a liquid, they're them sticking together. And strong IMFs between two things are a high solubility. And we will specifically talk about solubility here a couple times. I'm going to say the phrases. I don't necessarily have them written here as much. So when things dissolve, it is important to remember that we are breaking IMFs and we are making IMFs. And we have to think about both parts. So when salt and water are separate, the water's held together by hydrogen bonds, the salt's held together by ionic bonds. To get that to dissolve, I have to get the salts, the sodiums and chlorides separate. I have to get the waters to actually separate and make some room. When it makes salt water, there is an ion to dipole attraction. The water to the sodium to the water to the chloride to the water. That attraction between the ion and the dipole has to be at least as strong as the attractions that we're breaking in terms of solubility. The IMFs that you're breaking and the IMFs that you're making, if the new ones are as strong or stronger than the ones that you're breaking, the molecule wants to be mixed and it'll stay mixed. The instances where it doesn't mix is when that's not true. So like oil and water. Water sticks to water with hydrogen bonds. Oil sticks to oil with LDFs. Water sticks to oil with dipole to induced dipole. So that dipole to induced dipole is much weaker than the hydrogen bonds of water. Water will stay stuck to water. It won't mix. So when something doesn't mix, it's that new attraction isn't as strong as one or both of the attractions we had to break. So we've said that a lot. It's important to rehear that. Who knows if there'll be a solubility thing there. But when you're talking about the making and breaking of the INS, that's a good, key, complete, but kind of to the point way of describing it. So sorry, I just realized that I didn't know that later, and that was as good a time as any. And once again, I'll probably say it again later because the more you see and hear that. When you're asked about IMFs, you want to say what's the same, you want to say what's different. Okay, well, they're both covalent. This one has way more electrons than that, which is why its LDFs are stronger. They're both covalent. They both have a similar number of electrons. This one has LDFs. This one has hydrogen bonds. They're both covalent, different number of electrons. They both have this. This one has a much higher boiling point than that one. So what is the same and what is different? So almost always it says to list the IMFs for each, even if it doesn't say that you want to do that or need to do that. Molecule one, or this molecule has all of these LDFs. This molecule has all of these LDFs. When I mix them, these are the LDFs that they, or if I'm mixing them, these are the LDFs they have together. List every possible scenario there. Get to the point. Don't write sentences about it. Just say H2O equals all of its IMFs. This equals all of its IMFs. So that you have all the things that are similar and the things that are different. Focusing most of the time on the differences. The other thing, and we kind of started by talking about bonding, wanted to bring it back. With solids, IMFs are what are holding together molecular or generally a covalent solid. So covalent things are the things that end up melting really easily. Ice doesn't take that much energy relative to melt. Wax doesn't take that much energy to melt. Even sugar, we can heat that up and it will melt, not just dissolve in water. You add heat, it turns to a liquid, it melts. Ionic, metallic, and covalent networks stick together a lot more because every single atom is held in place by a relatively strong bond of some kind, ionic, metallic, or covalent bond. So I did want to come back around. It's less likely that it'll come up, but it's not that it won't come up. Covalent network solid, like diamond, like graphite, like sand. Things in the carbon family, if it's just a whole bunch of those, so not those mixed with hydrogen or oxygen or other elements, but just only carbons or just only silicons or silicon with oxygen, those are covalent network things that are held together by a repeating network of bonds. which is what gives them these different things. So once again, if we're going to be talking about properties or using data, sometimes we may just get a list of properties and then we kind of work our ways backwards. So molecular things, the covalent that are held together by IMFs, they don't conduct electricity because there's no ions moving around. They melt and boil very easily. Ionic compounds have high melting and boiling points. They are brittle because it's held by the ions needing to be in a certain arrangement. But once those ions do dissolve in a solubility situation, the free moving charges can conduct electricity. Metallic bonds are generally strong. They have high melting and boiling points for the most part. Sometimes they're kind of intermediately high, maybe not as high as ionic or covalent network. But because the electrons can freely move around, they do conduct. Because things can still rearrange themselves while being surrounded, they can. They're malleable and ductile. Covalent network solids are very strong bonds in all directions. They're rigid, they are hard. Diamonds, as our example, they can be semiconductors. So that's just in case, kind of a last thing related to IMFs. I listed today as gases and IMFs. With gases, there's not really a whole lot. There's less in terms of explanation, and we'll hit that a little bit on explanation day 2. We did the, together on our test just as a matter of bringing some math into the IMF day, but knowing that there's, or the IMF test, knowing that there's maybe less math, the IMFs is still #1 king of things to explain and understand well. So make sure you've got the key ideas, make sure you're looking at data. If solubility is still a mystery to you, go back to previous videos, check things out on the college board, send me a message. That's a good one to know. But in general, we know our strengths. We are using polarizability when we're talking about LDFs, but we're starting by just recognizing what IMFs do we have so that we can then compare their strengths using words like attraction and, other than hydrogen bonding, eliminating the word bond from explanation. We don't want them to misinterpret what we're saying going back and forth. So we still got a little bit more than a week. If this is tough, let me know and we can hit some specific details. Thanks.